So today I'm going to be giving a fairly broad overview of the Rust compiler. I won't be going terribly deep in any particular area, but I'll be covering a lot of different topics. I'm a member of FutureWay's Rust team. I first contributed to the compiler in 2016, and I'm currently a compiler team contributor and a member of the compiler performance and binary size working groups, and I have experience in a range of other compilers as well. So I'll start with a high-level overview of some things relating to the compiler. We often talk about a Rust toolchain, and this is several different programs that work together. And at the center you have the compiler itself. The compiler is called Rust-C, and being a compiler, its job is to translate Rust source code into executable code that you can then run on your machine. But people rarely run Rust-C directly. Usually they run it through Cargo, which is the Rust's build tool and package manager, and this is done through the familiar commands like cargo build and cargo test. Another important piece is the standard library. Most Rust programs use it, and the compiler is no exception. And then finally, to install all these pieces, you can use the program called Rust Up, which will install or update your toolchain. So Rust uses a train model release system, and the idea here is you have scheduled releases. Every 6 weeks there is a new version. The current version is 1.72, and the good thing about this schedule is you have very frequent and predictable releases, which means if you're working on a new feature and you're trying to get it into a particular version, but you're running a little bit late, if you miss the version that you were aiming for, it's not a big deal. It's only 6 weeks until the next one, so there's not that, you don't need to worry about getting something in when maybe it's not quite ready. And as a consequence of this, some Rust releases have big new features that are exciting, and some releases are not that exciting. They only have small improvements that a lot of people might not even notice. And so if I had to summarize this release model, I'd say it's good from an engineering point of view, but not quite as good from a marketing point of view. There are a lot of platforms supported by Rust, and the platforms are grouped into 3 tiers. Tier 1 is the ones that are guaranteed to work, and so there are 8 platforms in Tier 1, and these include some of the big ones that you might expect: x86-64 on Linux, Windows and Mac OS, and also ARM64 on Linux. Next we have Tier 2. These are guaranteed to build because we actually have CI infrastructure to build the compiler on these. But it's not guaranteed to necessarily run 100% correctly in all cases because we don't run tests regularly. And there are over 80 platforms in this category. And then Tier 3, where we have more than 120 platforms, is the platforms where we make no promises. We don't even promise that the compiler will build. We try to keep it building, and we won't deliberately break it, but the support level is quite low there. So the license, it's a dual MIT Apache 2.0 license. It's an open source license. It's very flexible. There's very few restrictions. So it's pretty simple. In terms of people and how people work on the compiler, the core team that works on the compiler has 15 people in it. They're the people who are primarily responsible for developing and managing the compiler's design and code. And then adjacent to that is the compiler team contributors, which is a group of currently 31 people, and these are also regular contributors to the compiler. And what these 2 teams have in common is that these are the people who can approve changes to the compiler. But of course, it is an open source project, and anybody can make a contribution to it. So the workflow is fairly simple. It's based around GitHub. The repository is on GitHub. All changes are made as GitHub pull requests. All changes require a review by a team member. That includes if a team member themselves makes a change, another team member has to review it. So there's nobody is more special than anybody else. All changes must pass CI testing before merge. This is really important. It ensures that the code in the repository is always in a good state and never broken. And then bugs and problems are reported via GitHub issues. So overall, it's a pretty standard and straightforward GitHub workflow. So that's some high-level things, and now I'll get a little bit into some of the compiler's internals. And the first thing to understand is that Rust-C is itself written in Rust, and this is done via a process called bootstrapping. And so the idea is version N of the compiler can be compiled with version N-1 of the compiler, and that can be compiled with version N-2, and so on back in time until you get to a point where something has to change. So the original Rust compiler was actually written in a different language called OCaml, and then once there was a working Rust compiler written in OCaml, then a new Rust compiler was written that was written in Rust, and then once you had that, then you could start this sequence of Rust being able to compile itself. But it's actually slightly more complicated than that, because once you have a working Rust version N compiler, you can then use that to build its own source code again, and so then you end up with Rust compiler version N that was compiled with itself, and that's actually what is released. So the Rust compiler that you are running on your computer was compiled by itself. So if you haven't heard of this process before, it's very confusing. It takes a little while to get used to, but it's actually a very standard compiler technique. So we're not doing anything particularly unusual here. The source code is structured quite nicely. There's more than 60 different crates within the compiler, covering all the sort of typical compiler things you might expect. If you know about compilers, you'll probably recognize some of the names here. You can see things like AST, CodeGen, error messages, lexing, parsing, and so on. And so what this means is if somebody who knows compilers comes in and they can look at this, and just by looking at the list, they can already immediately have a rough sense of where things are and how to find them. In terms of code size, there's a lot of numbers on this slide, but the important one is the one that I've put a green box around. So that's the number of lines of Rust code in the compiler, and it's almost 600,000. So it's a fairly big program. And when it comes to understanding the internals of a compiler, a really good way to approach it is to look at how does it represent code. And Rust has a number of different representations that it goes through. There's a lot to take in on this slide. I'm going to step through it one piece at a time, so you don't have to understand it all at once. And I will come back to this slide a number of times. So first of all, we can just ignore the internals and just remind ourselves that the compiler starts with Rust code, and then it does a whole lot of stuff, and then we end up with executable code. Then the first couple of steps now. So the first step is lexing. That's when we scan through the text of the source program. We break it into smallest possible chunks that make sense. That's things like identifiers and literals and punctuation. And so once we've done that, we have a stream of tokens. And then those tokens get fed to the parser, and it parses them and produces an abstract syntax tree, or an AST. And the AST is a tree data structure that is very close to the original source code. Almost everything in the original source code is effectively present in that tree. And once we have the AST, we do several important operations on it, and that includes macro expansion and name resolution. Once we've finished with the AST, we do a step called lowering, and that produces here, or high-level intermediate representation. This is another very important representation. It's a little bit more low-level than the AST. Certain language features have been removed at this point. And that's the level at which we do type checking and type inference and trait solving, which are all quite important operations. Then there's another lowering step to what we call typed here, and this is the level at which we do a couple more steps, including pattern checking and exhaustiveness checking. There's one more lowering step, and we end up with MIR. This is the mid-level intermediate representation. This is a control flow graph type structure, and a lot of important stuff happens here. Borrow checking happens here, which is obviously crucial. And if you've ever programmed Rust, you might have noticed that you have to fix all your type errors before you get any borrow check errors. And the reason for this is you can see that the borrow checking happens at a later stage. So the compiler does some optimizations on MIR. These are some of the classical sort of data flow optimizations, things like constant propagation, copy propagation, and dead store elimination. There's also a certain amount of inlining that gets done at this point. And then the final important thing about MIR is that this is the point at which monomorphization happens. So if you have a generic function and it's instantiated for several different types, this is where that function will get instantiated in that way, duplicated. Now we're up to the final couple of steps. So the first code generation step takes the MIR and produces LLVM IR. LLVM is the compiler backend that Rust uses. It's very well known. It's used by a lot of different projects, and it's generally very high quality. So then we hand the code to LLVM. It does a lot of optimizations. We rely heavily on the fact that it does a very good job at this. And then once it's finished doing its optimizations, LLVM itself will then generate the final executable code. Okay, so that's given you an idea of all the different steps. We've got 5 representations within the compiler itself, plus LLVM IR, which is used by LLVM. So it's quite a few steps, but this is not that unusual for compilers. It's the general sort of trend. You start with high-level representations that are close to the source code, and then you gradually get lower and lower until you end up with something at the machine code level. So the next topic is queries. So a traditional compiler has multiple fixed passes, but Rust is a little different. A lot of it is based around these function-like queries that compute certain types of information. So for example, there's a type of query that will compute the type of a function. And the results of queries are memoized, which means that you compute them once and then they get stored in a table. So then if you call type of on a function, it will be computed the first time. If you then do it again, it will just not recompute the stuff. It will just look it up in the table. And a big reason for this is that that's how incremental compilation works. Incremental compilation is the language feature the compiler feature where if you compile new code for the first time, it will take a certain amount of time. And then if you make a small change and recompile, it will be much faster because it's able to reuse a lot of information from the previous compilation. And this is built on top of the query system, and that query table is effectively saved to disk and a lot of it's able to be reused. So a couple of things about memory management. We use interning heavily. This is a technique where you store one copy of each unique value. It's very often used for strings, but we also use it for some internal types within the compiler for representing language types and lifetimes, for example. The good thing about this is it reduces memory use. If you only have, it's obviously cheaper in terms of memory to store each unique value once instead of possibly having duplicates. It also means you can have cheaper quality comparisons because you can just look at the address of an intern value and to decide whether 2 different intern values are the same or not. The downside of interning is that when you want to create a value, it's a little bit on the slow side because you have to do a hash table lookup to see, is this a new value or is it one that I've seen before? We also use arenas a lot. So this is a memory allocation technique. Basically, the idea is you have an arena to which you can allocate lots of small things separately, but then at some point you free all of them at once. And that's a pretty common technique. Again, compilers use arenas quite a lot. So parallelism is an interesting topic. So there's a lot of parallelism that comes from outside the compiler at the interprocess level, thanks to Cargo, because Cargo can create can set multiple Rust-C processes running at the same time. And here's a diagram that sort of visualizes this. So this was from a visualization of the compilation of the program ripgrep, a text search program that's very popular. Each line on this picture represents the compilation of one crate, and each one of these is a separate Rust-C process. And you can see, and time is represented on the x-axis, so you can see some of them didn't take very long, some of them took longer. And you can also see the first 26 or so of them all started at the same time, and so they were all compiling in parallel. So this was on a machine with a lot of cores, so it was able to compile 26 crates at the same time. And then the last few, you can see they didn't start until a little bit later on, probably because there were some dependencies and some of the earlier crates needed to be finished compiling before these later crates could start. So for these first 31 crates, you can see there's a lot of parallelism going on. But now here's the second half of the compilation for this program. And you can see as it gets towards the end, there's a lot less parallelism available. And that's just got to do with which crates depend on which others and so on. There you can see there are some points in this sequence where there was only one crate compiling at a time. And this is a pretty common pattern that you start off with a lot of parallelism early on, and then as you get towards the end, you tend to have less. So Cargo gives you a good amount of parallelism, but not you need something else to get to take full advantage of multiple cores. And so therefore the compiler also has a certain amount of parallelism inside the compiler. The main way that works currently is that we take advantage of LLVM, can do code generation in parallel. So if you break your code up into chunks and then you hand those chunks to LLVM, it can do code generation and optimization on each chunk in parallel. And we take advantage of that. And we're also in the process of adding parallelism to the front end of the compiler, but that's not yet available in the released code. And this picture demonstrates those 2 points quite well. So this is the output of a profiler called Samply. Each line on this picture represents a thread of execution. You can see at the bottom we have a thread called Rust-C. That's the main thread, and that's running for almost the entire program. Then on the right-hand side, you can see we have a lot of short-running threads. So that's LLVM doing its thing. I think we've got about 16 different threads going there, and you can see quite a lot of them overlap, so there's a good amount of parallelism happening there. But then on the left-hand side of the red line, that represents the front end, there's no parallelism. And like I said, we're in the process of adding that. Hopefully that will happen this year. So Rust-C is famous for producing good error messages, and it produces good error messages. This is not by accident. A lot of people spend a lot of time and effort going into this, and because they really care about it. And it's quite important because Rust is not the easiest language to learn, and so good error messages can really make Rust programmers' lives a lot easier. Here's an example of an error message. I won't step through every detail here, but what's worth noticing is that this is the error message for one error. So there's quite a lot of detail and explanation. This is a type error. It tells you, I expected this type, I saw this type, and then at the bottom it even tells you how you could easily fix the problem, which is really nice. So error messages are currently only in English, but there's a long-term project underway to provide translations to other languages. And this will make Rust easier to use for many people, and I think is quite important. So when it comes to backends, I mentioned the LLVM backend. That's the one that is currently used in production releases. As Josh mentioned, there are a couple of other backends under development. CraneLift, and the motivation for CraneLift is that it's faster, the quality of the code, it does fewer optimizations, but for debug builds, you might end up with faster compile times, and so that could be a good thing. And then for GCC is the other backend. of note, and the motivation here is that GCC supports some platforms that LLVM does not. So a couple of other things. So when it comes to testing, there are several test suites in the compiler. They cover a variety of functionality, errors, code generation, debug info, and so on. There are more than 20,000 test files and actually over 500,000 lines of code. I was quite surprised when I measured this. It was more than I expected. And that's, you might remember, we had 600,000 lines of code for the compiler itself, and then we have 500,000 lines worth of tests. We care a lot about the compiler's performance. We have a benchmark suite called Rust C Perf that has more than 40 benchmarks in it. That gets measured on every single merge, and the results from that measurement get posted into the GitHub pull request. So that means that a pull request author always knows very soon after the merge happens whether they improved performance or regressed it. And it's also possible before you do a merge to measure this as well if you think that it's going to have an effect on performance. And there's also a website that has detailed performance history available that you can look at. Another interesting topic is breaking changes. So in Josh's talk, he talked about Rust's strong backwards compatibility guarantees. Now these are not utterly 100%. There are some cases where we might need to fix a compiler bug or fix a language soundness issue in a way that could cause existing code. The code that compiles currently might get broken and stop compiling. This is obviously would be an inconvenience, and we have a really useful tool to evaluate whether a change is likely to cause problems. And it's called Crater, and what it does is you can give it a particular version of the compiler, say you've fixed some little bug, and it will then run that version of the compiler on every crate on crates.io, and there are over 125,000 crates there. That's most of the crates that are publicly available. And then Crater will then collect results and tell you what's changed in the version of the compiler that you just tested. Are there crates compiling that used to not compile, or are there crates not compiling that used to compile? And so sometimes if you're lucky, there's no changes, or maybe there's a very small number of changes in some crates that are not very widely used, and so that's easy to go forward. Sometimes you might have a problem where some popular crate is broken, or perhaps a large number of crates are broken, and then you have to be a lot more careful about fixing this problem. You might need to issue warnings for quite a while before you then upgrade it to a full error. There are a few other tools that share code with the compiler. One is RustDoc. It's the tool that generates documentation from doc comments. Another one is Miri. It's a Mir interpreter. So Mir is one of those intermediate level representations I talked about before. It's useful for if you're writing unsafe code, it can detect bugs within that unsafe code. And then Clippy is a linting tool. So it can evaluate your code and tell you if there are ways that you could improve it. And they all share a lot of code with the compiler itself. So that brings me to the end. So Rust C, it's a fairly large and complex and sophisticated compiler. But having said that, I find it personally surprisingly easy and enjoyable to work on, given that it is so large. And I think a lot of that is that Rust is a really great language for writing compilers. It's a good language in general, but for compilers in particular, it's really good. I think algebraic data structures and pattern matching are two killer features for compilers. But just in general, speed, safety, control, and expressiveness. I've worked on compilers in a number of different languages, and Rust is definitely my favorite. And finally, if you have enjoyed hearing about the compiler and you want to know more, I can strongly recommend the Rust C Developer's Guide. It has a lot of details, gets into the nitty-gritty of the code, and is a really good starting point for if you are interested in contributing to the compiler. And that's the end of my talk. Thank you very much.
Oh. Thank you, Nicholas. Please stay for Q&A session. 大家有问题吗？有没有问题可以现场提问？
So, as you were describing the Rust C bootstrap process, I was thinking about how that interacts with Josh's talk about Rust in 2051. Are we going to be continually bootstrapping ever linearly increasing quantities of Rust versions, or in the future, do you see that there could be a way to skip some gaps, or to say build a more modern version of Rust off of a totally different starting point?
Okay, so the question's about bootstrapping and Rust editions in the long term. So I described that bootstrapping process going all the way back to the original Rust compiler, but that's not, just in case that wasn't clear, that's not something that's happening on any regular basis.
So you could technically do it, but there's no reason to bother.
Yeah, you would never bother. Yeah, you could compile all the way back to 1.1 and then earlier versions, but you never would. So you can certainly. I think the compiler has. It's a good question. I think the compiler's crates are probably a mixture of different editions, or maybe somebody brings them up to date. I'm not sure. I don't foresee any problems if that helps.
对，还有问题没有？如果没有问题，我们就再次感谢 Nicholas。Once again, thank you, Nicholas.